This video gives a brief overview of the microwave optics experiment. A rule of thumb for doing diffraction and interference experiments with electromagnetic radiation is that the wavelength of the radiation should be roughly similar to the size of the structure that is being studied. So for example, if you want to do a diffraction experiment, X-ray diffraction off of a crystal, then your wavelengths need to be of order 10 to the minus 10 meters or so, because that's the spacing between the atoms in a crystal. Similarly, if you want to do two-slit diffraction, then the wavelength of the radiation is sort of similar to the spacing between the slits. What we'd like to do in this experiment is diffraction and interference experiments with structures that are macroscopic. So for example, we're going to be doing two-slit diffraction with these as our two slits. We're going to do an interference experiment, Bragg scattering off of a crystal. I don't know if you can see it very well, but these are kind of ball bearings that are suspended inside of a styrofoam cube. And we're going to be scattering off of this crystal. We also are going to do a Fabry-Perot experiment, and our planes in the Fabry-Perot experiment will be several centimeters apart. They're going to be mounted to these guys, and you can just see them behind here. Okay, the reason we can do this is because even though these structures are sort of on the scale of centimeters, the wavelength that we're going to use is also of order a few centimeters. In fact, we're going to be using microwaves, and the wavelength of the microwaves we're using is approximately 2.85 centimeters. Before we get started, I want to mention a few precautions and notes. We're going to be using microwaves, and the experiment is generally safe, but you do need to make sure that you don't put your head in the way of the transmitter horn here. Okay, so don't try to look inside the horn, or when you're making angular measurements down here, make sure that this is unplugged. Okay, unplug the transmitter every time that you put your head down here to look at the scale. And as lab partners, you need to try to help each other to remember to do that. You also should not put your hand in the way of the transmitter or the receiver. You shouldn't be anywhere near this when this is transmitting radiation. Another thing is that if you have a pacemaker or another electronic medical device, then you should not do this experiment. This experiment could be dangerous for you if you have an electronic medical device. Something which you probably don't need to worry about, but the polarization angles of the transmitter and receiver need to be set to be in alignment. Basically this and this is the transmitter, this is the receiver. These can be rotated about this axis to study polarization effects. Okay, and then finally, you should note that microwaves will reflect off of other things in the vicinity. So for example, if you're wanting to do a two-slit diffraction through these two slits here between these metal plates, you're really just wanting to look at the waves that are transmitted between these plates and then interfere with each other on the other side here. You don't really want to be looking at something that gets emitted this way, bounces off some piece of metal that might be sitting here, and then bounces over here into your receiver. So these microwaves will be reflected off of things that are metal particularly, but other things as well. You want to be clear of this whole region here and make sure the work area is clear, so that you're not getting spurious reflections that are not what you want to be studying. You're going to be doing 3 separate experiments with the microwave transmitter and receiver. The first is a two-slit diffraction experiment. So in this experiment, you'll have the transmitter emitting microwaves, which will be hitting these 3 metal plates here with 2 slits between them. And then you'll take the transmitter. The transmitter can actually rotate like that about the axis, and you'll measure the intensity, which will show up as a voltage reading. So the voltage as a function of this angle here, or on this side, either way. Just to review some of the physics behind two-slit diffraction, let's do that for a second. So in two-slit diffraction, we imagine that we have essentially plane waves coming in with wavelength lambda. They come in, they hit the barrier here with the slits in it. The slits are distance d apart. And then on the other side, we get these sort of circular waves emitted from the slits, and when a peak of the wave hits a peak of the wave coming from the other slit, then we get constructive interference, and when a peak hits a valley on the other side, we get destructive interference. And what we see is that if we had a screen or something that we could project the radiation onto, then we would see that we get these interference maxima and minima. So this is a typical interference pattern here. If we define theta to be the locations where we get maxima, then it turns out that the maxima obey what's called the two-slit diffraction formula. So theta is the angle at which the maxima occur, d is the slit spacing, lambda is the wavelength, and n is the order of the maximum. So this is n equal to 0, this is n equal to 1, n equal to 2, etc. So you'll be finding 3 maxima and doing fits to the peak as described in the lab description, and in order to check the two-slit diffraction formula. You're also going to compare your measured values for theta with the expected values. You don't need to propagate errors for this experiment. Just calculate the percent difference between the expected and the measured values of the angles. The next experiment we're going to talk about is called Bragg scattering. So Bragg scattering is a type of interference that happens when radiation scatters off of planes in a crystal. So imagine that each of these dots represents an atom in a crystal, and as you can see, there are various planes. So there's a set of what are called Bragg planes, but there are other Bragg planes as well. For example, here's another set of Bragg planes. Let's focus on the first set of planes that I drew. So imagine that we've got radiation that comes in. In particular, let's take a look at two parallel rays here that are coming in. This ray hits the top plane and reflects off. The ray parallel to it hits the next plane and reflects off. We'll take this angle to be theta. Actually, we'll have theta be on both sides there, and then this is theta as well. So the question is, what is the condition such that the rays, which started out in phase with each other here, are still in phase with each other when they bounce off? And if you think about that for a little bit, what you'll see is that if we draw a line here that's perpendicular to the ray, and a line here that's perpendicular to the ray, what we're interested in is this distance right here, that plus that. And as you can guess, the sum of those two, each of those, this distance here between the Bragg planes is d. Geometrically, this distance right here is d sine theta, as is that one right there. So the requirement that there be constructive interference is that d sine theta times 2, so 2d sine theta, has to be equal to an integer number of wavelengths. So 2d sine theta is equal to n lambda. This is called the Bragg scattering formula. Notice that it looks very similar to the two-slit diffraction formula, except that this expression has a 2 here, which was not present for the two-slit diffraction formula. Okay, so this is one condition to have constructive interference. The other condition is that these two thetas here have to be the same as each other, the incident angle and the reflected angle theta. Okay, so those two conditions together allow us to have constructive interference. Let's take a look at the experimental setup here for a second, because the fact that this angle here and this one here have to be equal to each other has an important effect in our experiment. So imagine that we've got our transmitter here, and it's sending out radiation like so and reflecting off of one of these Bragg planes, or several of them actually, and then scattering here into our receiver. The important thing is that this angle here, theta, has to be equal to this angle here, also theta. But what that means is that every time you take the block, the crystal with the steel ball bearings in it, and you rotate it by an angle theta, then you have to rotate the receiver by an angle 2 theta, because this angle right here is also theta. Okay, so this is 2 theta. So what that means is that you're going to take a measurement with, well, first you'll start with the block being just parallel, so theta being 0. Then you're going to rotate the block by, say, a couple of degrees. That would be this angle here. And then you're going to rotate the receiver by twice as large of an angle. So every time you rotate the block by 2 degrees, you're going to rotate the receiver by 4 degrees, etc. That's in order to maintain the Bragg condition that this angle is equal to that angle. In this experiment, you're going to use your measured values for theta, the known value for lambda, to determine an experimental value for what d should be, the spacing between the planes, and then you can actually measure the spacing between the middles of the ball bearings, the spacing between the planes, and you'll compare those and calculate the percent difference. As with the previous experiment, the two-slit diffraction, there's no error propagation required here. You'll be calculating a percent difference. The third experiment is called the Fabry-Perot interferometer. And in a Fabry-Perot interferometer, we have a transmitter and a receiver, and then 2 barriers. But these barriers are not completely reflecting barriers, so there's some amount of transmission that is allowed through the barrier. So imagine that we have some initial wave that's sent out from the transmitter, and part of the wave gets reflected, but part of it gets transmitted. And then when that wave gets to the second barrier, part of it gets transmitted and part of it is reflected. And when that gets back to the first barrier, part of it is transmitted and part of it is reflected. And then when it gets over to the right barrier again, part of it can be transmitted and part reflected, and we get these multiple reflections and transmissions. Okay, so it turns out that the transmitted signal over here is the largest when all of these transmitted waves are in phase with each other. And that's the situation that we're looking for. So what we're going to be doing is we're going to leave this guy fixed, and we're going to allow this guy, we're going to move it left and right. And we're looking for a position where we get maximum transmission, which means that the waves are in phase with each other. Okay, so it turns out that if this distance here between the 2 barriers is L, then this maximum transmission occurs when L is equal to n lambda over 2, meaning there are a half integer number of wavelengths in between the two barriers. So this is L right here. Okay, so what you're going to be doing then is you're going to move the right barrier back and forth and look for maxima. And what you should see is that as you move it slowly, say you're leaving this guy fixed and move this guy slowly towards the right, you should see that you have periodic maxima and minima in the signal that you're receiving over here on the right, and that the cycle is repeating every half wavelength. So the wavelength is 2.85 centimeters, so you should be seeing transmission maximum approximately every 1.42 or 1.43 centimeters. The lab manual describes how you can use the transmission maxima to determine the wavelength of the microwaves. Instead of following that procedure though, you can actually just set up the experiment and then call me over and show me that the maxima are the correct distance apart from each other, just to show that it's working. And this will be just sort of a checkpoint like you did in university physics, rather than following the lab description as it is in the lab manual. That's it. So follow the format of lab reports for writing up your lab. Don't forget to do sample calculations, and to conclude with a final discussion and conclusions section. If you like, you can have 3 separate discussion and conclusion sections for the 3 experiments. For the Fabry-Perot interferometer, because you're not doing the full analysis that's described in the lab manual, what you just need to do is write 1 paragraph explaining what it was that you saw, explaining the point of that little experiment and what you observed.